Hello everyone, let's read Chapter 4 Pharmacodynamics Mechanism of Drug Action Receptor Pharmacology. Competency covered is describe general principles of mechanism of drug action. Pharmacodynamics is the study of drug effects. It starts with describing what the drug does and goes on to explain how they do it. Thus, it attempts to exclude the complete action effect sequence and the dose effect relationship. The modification of the action of one drug by another drug is also an aspect of pharmacodynamics. Principle of drug action. Drugs, except those gene based, do not impart new functions to any system, organ, or cell. They only alter the pace of ongoing activity. However, this alone can have profound medical as well as toxicological impact. The basic types of drug action can broadly be classified as first, stimulation. It refers to selective enhancement of the level of activity of specialized cell. For example, adrenaline stimulates heart, pilocarpine stimulates salivary glands. However, excessive stimulation is often followed by depression of that function. For example, high dose of picrotoxin, a central nervous system stimulation, produces convulsions followed by coma and respiratory depression. Second, depression. It means selective diminution of activity of specialized cell. For example, barbiturates depresses CNS, quinidine depresses heart, omeprazole depresses gastric acid secretion. Certain drugs stimulate one type of cells but depresses the other. For example, acetylcholine stimulates intestinal smooth muscles but depresses the SR node in heart. Third, irritation. This connects a non-selective, often noxious effect and is particularly applied to less specialized cell epithelium connective tissue. Strong irritation results in inflammation, corrosion, necrosis, and morphological damage. Replacement. It refers to the use of natural metabolites, hormones, or their congeners in deficiency states. For example, levodopa in Parkinsonism, insulin in diabetes mellitus, iron in anemia. Fifth, cytotoxic action. Selective cytotoxic action on invading parasites or cancer cells, attenuating them without significantly affecting the host cell, is utilized for cure or palliation of infection and neoplasms. For example, penicillin, chloroquine, zidovudine, cyclophosphamide, etc. Abbreviations: AA amino acid, AC adenylyl cyclase, ANP atrial natriuretic polypeptide, BAL British anti-leukocyte, CAM calmodulin, CAMP cyclic adenosine monophosphate, CGMP cyclic guanosine monophosphate, CREB cyclic AMP response element binding protein, DAG diacylglycerol, DHAF dihydrofolic acid, DMCM dimethoxyethyl carbomethoxy beta carbolane, DRC drug response curve, EDTA adenylene diamine tetraacetic acid, EGF epidermal growth factor, GABA gamma aminobutyric acid, GC guanylyl cyclase, GDP, guanosine diphosphate, GPCR, G protein coupled receptor, GTP, guanosine triphosphate, HMG CoA, 3-hydroxy 3-methyl glutaryl coenzyme A, HSP, heat shock protein, 5-HT, 5-hydroxytryptamine, IA, intrinsic activity, IP3, inositol 1,4,5 triphosphate, JAK, genus kinase, MLCK, myosin light chain kinase, NGF, nerve growth factor, NO, nitric oxide, PDE, phosphodiesterase, PIP2, phosphatidyl inositol 4,5-bisphosphate, pKa, CAM dependent protein kinase, PLCs, phospholipase C, RTKs, receptor tyrosine kinase, SLCs, solute carrier, SSRI, selective serotonin reuptake inhibitor, STAT, single transducer and activator of transcription, TGF, transforming growth factor. Now let us see mechanism of drug action. Only a handful of drugs can act by virtue of their simple physical or chemical properties. For example, bulk laxatives, isabgol, physical mass, petroleum jelly, lubricant, para-aminobenzoic acid, absorption of UV rays, activated charcoal, adsorption property, mannitol mag sulfate, osmotic activity. 131I and other radioisotopes radioactivity, antacids neutralization of gastric HCl, potassium permanganate, oxidizing property, chelating agents, edita dimercaprol, chelating of heavy metals, cholestyramine, sequestration of bile acids and cholesterol in the gut, MESNA, scavenging of vesicotoxic reactive metabolites of cyclophosphamide. Majority of drug produces their effect by interacting with discrete target biomolecules, which usually are proteins. Such a mechanism confers selectivity of action to the drug. Functional properties that are targets of the drug action can be grouped into 4 major category-wise: enzyme, ion channels, transporters and receptors. However, a few drugs do act on other proteins: colchicine, vinca alkaloids, taxanes binds to the structural protein tubulin or on the nucleic acid. Alkylating agents, substrate inhibitor, enzyme, product, no product, functional, no product or non-functional product, blocker, opener, modulator, channel, ion, substrate, transporter, inhibitor, competitive antagonist, non-competitive antagonist, agonist, transducer, effector. 4 major types of biomacromolecule targets of the drug action are enzyme, transmembrane ion channels, membrane-bound transporter, and receptor. First is enzymes. Almost all biological reactions are carried out under catalytic influence of enzymes. Hence, enzymes are very important target of drug action. Drugs can either increase or decrease the rate of enzymatically mediated reactions. However, in physiological systems, enzyme activities are often optimally set. Thus, stimulation of enzyme by drugs that are truly foreign substances is unusual. Enzyme stimulation is relevant to some natural metabolites only. For example, pyridoxine acts as a cofactor and increases decarboxylase activity. Several enzymes are stimulated through receptors and second messengers. For example, adrenaline stimulates hepatic glycogen phosphorylase through beta receptors and cyclic AMP. Stimulation of an enzyme increases its affinity for the substrate so that the constant rate of the reaction is lowered. Enzyme stimulation, enzyme induction, normal, competitive inhibition, non-competitive inhibition. Km and Vmax and half Vmax value, reaction velocity and substrate concentration. Effect of enzyme induction, stimulation and inhibition or on kinetics of enzyme reaction Vmax, maximum velocity of reaction, Vmax substrate of stimulated enzyme, Vmax 1 in the presence of non-competitive inhibitor, Km rate constant of the reaction, Kms of stimulated enzyme, Km1 presence in the competitive inhibitor. Enzyme induction and non-competitive inhibition do not change the affinity of the enzyme. Km is unaltered, whereas enzyme stimulation and competitive inhibition respectively decreases and increases the Km. Apparent increase in enzymatic activity can also occur by enzyme induction, that is, synthesis of more enzyme protein. This cannot be called stimulation because the Km do not change. Many drug-induced microsomal enzymes. Enzyme inhibition. Some chemicals, heavy metal, salts, strong acids and alkali, formaldehyde, phenol, etc. denature the proteins and inhibit all enzyme non-selectively. They have limited medicinal value, restricted to external application only. However, selective inhibition of a particular enzyme is a common mode of drug action. Such inhibition is either competitive or non-competitive. First, competitive equilibrium type. The drug is being structurally similar, competes with the normal substrate for the catalytic binding site of the enzyme so that the product is not formed or a non-functional product is formed, and a new equilibrium is achieved in the presence of the drug. Such inhibitor increases the Km, but the Vmax remain unchanged. That is, higher concentration of the substrate is required to achieve half the maximal reaction velocity, but if the substrate concentration is sufficiently increased, it can displace the inhibitor and so maximal reaction velocity can be attained. Some examples of competitive enzymes inhibitor are listed in table 4.1. Some enzymes, their substrate and competitive inhibitors. Enzyme, endogenous substrate, competitive inhibitors. Choline esterase, endogenous substrate acetylcholine, competitive inhibitor physiostigmine and neostigmine. So enzyme is choline esterase, endogenous substrate is acetylcholine, and inhibitor is physiostigmine and neostigmine. Monoamine oxidase MAO-A, endogenous substrate is catecholamine and inhibitor is moclobemide. Dopa decarboxylase, endogenous substrate is levodopa and competitive inhibitor is carbidopa and benzerazide. Then xanthine oxidase endogenous substrate is hypoxanthine and enzyme inhibitor is allopurinol. Angiotensin converting enzyme angiotensin 1 is endogenous substrate and competitive inhibitor are captopril, enalapril and ramipril. Enzyme is 5-alpha reductase. Endogenous substrate is testosterone. Competitive inhibitor is finasteride. Enzyme is aromatase. Endogenous substrate is testosterone, endostenedione, and competitive inhibitor is letrozole, anastrozole. Enzyme is bacterial folate synthase. Substrate is para-aminobenzoic acid and inhibitor is sulfadiazine. Non-equilibrium type of enzyme inhibition can also occur with the drug which react with the same catalytic site of the enzyme but either have strong covalent bond or have such high affinity for the enzyme that the normal substrate is not able to displace the inhibitor. For example, organophosphates react covalently with the esteric site of the enzyme cholinesterase. Methotrexate has 50,000 times higher affinity for dihydrofolate reductase than the normal substrate DHFA. In this situation, Km is increased and Vmax is reduced. Second, non-competitive. The inhibitor reacts with an adjacent site and not with the catalytic site but alters the enzyme in such a way that it loses its catalytic property. Thus, Km is unchanged but Vmax is reduced. For example, table 4.2, some non-competitive enzyme inhibitors, enzyme carbonic anhydrase, non-competitive inhibitor acetazolamide for cyclooxygenase, aspirin, indomethacin for aldehyde dehydrogenase disulfiram, for H plus K plus ATPase omeprazole, Na plus K plus ATPase digoxin, phosphodiesterase theophylline, thyroid peroxidase profylthiouracil, HMG-CoA reductase lovastatin, and phosphodiesterase sildenafil. Ion channel. Protein which act as an ion selective channel precipitate its transmembrane signaling and regulates the intracellular ion composition. It precipitates its transmembrane signaling and regulates the intracellular ion composition. This makes them common target for drug action. Drug can affect ion channels, some of which actually are receptors because they are operated by specific signal molecules either directly and are called as ligand-gated channels. Nicotinic receptors in the figure 4.4 or through G protein and are termed as G protein regulated channels. For example, cardiac beta adrenergic receptors, activated calcium channels. Drugs can also act on voltage-operated and stretch-sensitive channels by directly binding to the channel and affecting ion movement through it. For example, local anesthetics which obstruct the voltage-sensitive sodium channels. In addition, certain drugs modulate opening and closing of the channels. For example, quinidine blocks the myocardial sodium channels. Dofetilidine and amiodarone blocks myocardial delay rectifier potassium channels. Nifedipine blocks L-type of voltage-sensitive calcium channels. Nicorandil opens ATP-sensitive potassium channels. Sulfonylureas inhibit pancreatic ATP-sensitive potassium channels. Amiloride inhibits renal enzyme sodium channels. Phenytoin modulates prolongs the inactivated state of voltage-sensitive neuronal sodium channels. Transporters. Several substrates are translocated across the membrane by binding to specific transporters. Carriers which either facilitate diffusion in the direction of the concentration gradient or pump the metabolite or ion against the concentration gradient using metabolic energy. Many drugs produce their action by directly interacting with solute carrier class of transporter protein to inhibit the ongoing physiological transport of the metabolite or ion. Examples are Dazipramine and cocaine block neuronal reuptake of noradrenaline by interacting with norepinephrine transporter. Fluoxetine and other SSRIs inhibit neuronal reuptake of 5-hydroxytyrosine by interacting with serotonin transporters SERT. Amphetamines selectively block dopamine reuptake in brain neurons by dopamine transporters. Reserpine blocks the vesicular reuptake of noradrenaline and 5-hydroxytyrosine by the vesicular amine transporter VMAT2. Tiagabine acts by inhibiting reuptake of GABA into the brain neurons by GABA transporter GAT1. Furosemide inhibits the sodium-potassium 2 chloride co-transporter in the ascending limb of loop of Henle. Hydrochlorothiazide inhibit the sodium chloride symporter in the early distal tubule. Probenecid inhibits active transport of organic acid, uric acid and penicillin in the renal tubules by interacting with organic anion transporter OAT receptors. The largest number of drugs do not bind directly to the effectors, viz. Enzyme channels, transporters, structural proteins, template biomolecules, etc., but act through the specific regulatory macromolecules which control the above listed effectors. These regulatory macromolecules or the site on them which associate with and interact with the drug are called as receptors. Receptors is often asked as an question. Receptor, it is defined as a macromolecule or binding site located on the surface or inside the effector cell that serves to recognize the signal molecules or drugs and initiate the response to it, but itself has no other function. though in a broad sense all types of target biomolecules, including the effectors, enzymes, channels, transporters, etc., with which a drug can bind to produce its action, have been denoted as receptors by some authors. Such designation tends to steal the specific meaning of this important term. If so applied, xanthine oxidase would be the receptor for allopurinol. L-type calcium channel would be the receptor for nifedipine. Serotonin transporter SERT, not in consonance with general understanding of the term receptor. It is therefore better to reserve the term receptor for purely regulatory macromolecules which combine with and mediate the act of signal molecules, including the drug. The following terms are used in describing the drug-receptor interaction. Ligand, Latin liger, which means to bind. Any molecule which attaches directly to particular receptors or site. The term only indicates affinity or ability to bind without regard to functional change. Agonists and competitive antagonists are both ligand of the same receptors. Agonist, an agent which activates a receptor to produce an effect similar to that of an physiological signal molecules. Inverse agonist, an agent which activates a receptor to produce an effect in an opposite direction to that of agonist. Partial agonist, an agent which activates a receptor to produce submaximal effect but antagonizes the effect of the full agonist. Antagonist, an agent which prevents the action of an agonist on the receptor or the subsequent response but does not have any effect of its own. The overall scheme of the drug action through the receptor is depicted in figure. In silico docking techniques based on structural features are being used to identify newer ligands for proposed or postulated binding sites or targets. In silico screening is used for this purpose by pharmaceutical industry to identify new targets and corresponding ligands. Receptor occupation theory. After studying quantitative aspect of a drug action, Clark in 1937 propounded a theory of drug action based on occupation of receptor by specific drug, and that the pace of cellular function can be altered by interaction of these receptors with drug, which in fact are small molecular ligands. He perceived the interaction between the two molecule species wise drug and receptor to be governed by the law of mass action and the effect to be the direct function of drug receptor complexes formed. D plus R K1 K2 dr gives E. Subsequently, it was realized that occupation of the receptor is essential but not itself sufficient to elicit a response. The agonist must also be able to induce a conformational change in the receptor. The ability to bind with the receptor designated as affinity and the capacity to induce the functional change in the receptor designated as intrinsic activity or efficacy are independent properties. Affinity of a drug for a receptor determines its concentration around the receptor required to form a certain number of drug receptor associations. Higher affinity implies that the same number of drug receptors will be formed at the lower concentration of the drug compared to another drug which has the lower affinity. Intrinsic activity of a drug is the measure of its ability to induce the functional change in the receptor, which could vary from 0 to 1, nil to maximal. Competitive antagonists occupy the receptor but do not activate it, while certain drugs are partial agonists which occupy and submaximally activate the receptor. An all or none action is not a must at the receptor, a theoretical quantity S denoting the strength of stimulus imparted to the cell as was interposed in the Clark equation, where drug plus receptor K1 K2 gives drug receptor complex which eventually gives S and E. Depending upon the agonist, drug receptor complex could generate a stronger or weaker strength of stimulus, probably as a function of degree of conformational change brought about by the agonist in the receptor. Accordingly, agonists have both affinity and maximal intrinsic activity. Intrinsic activity is 1. For example, adrenaline for adrenergic receptor, morphine for opiate microreceptor. Competitive antagonists have the affinity but no intrinsic activity. For example, atropine on muscarinic receptor, naloxone on micro-opiate receptor. Partial agonists have affinity and submaximal intrinsic activity between 0 and 1. Example, pindolol for beta-adrenergic receptors, buprenorphine on micro-opiate receptors. The low ceiling response to a partial agonist is not because of lower affinity for the receptor. In fact, some partial agonists have higher affinity and are dose to dose more potent than the full agonists. For example, buprenorphine is 25 times more potent than morphine, full agonist of micro-opioid receptor, but is a partial agonist and cannot relieve very severe pain or deeply depress respiration. Partial agonists antagonize the effects of a full agonist, but they occupy a large population of the receptor while producing small response and leave fewer receptors to interact with the full agonist. As such, buprenorphine participates withdrawal syndrome is a highly morphine-dependent subject but can substitute for it at lower level of morphine dependence. Inverse agonists have affinity but intrinsic activity with a minus sign IA between 0 and -1. Inverse agonism is manifest only in case of some receptors which show certain degree of constitutive action, that is, they are partially active even in basal state, complete absence of any agonist. In other words, they are tonically active. Benzodiazepine receptors is one such receptor and DMCM is its inverse agonist. The beta-adrenergic receptor blockers propranolol and carvedilol have also shown weak inverse agonist activity of beta receptors. It has also been demonstrated that many full agonists can produce maximal response even while occupying less than 1% of the available receptors. A large receptor reserve exists in their case, or a number of spare receptors are present. On the other hand, for certain drugs, the total number of receptors may limit the maximal response and there is no space receptors. The two-state receptor model. An alternative two-state receptor model for explaining the action of agonists, antagonists, partial agonists, and inverse agonists has been proposed. The receptor is believed to exist in two interchangeable states, Ra, which is active, and Ri, which is inactive, which are in equilibrium. In case of majority of the receptors, the Ri state is favored at equilibrium. No or very weak signal is generated in the absence of agonists. The receptor exhibits no constitutive activation. The agonists bind preferentially to Ra conformation and shifts the equilibrium. Ra predominates and the response is generated. The competitive antagonist B binds to Ra and Ri with equal affinity. The equilibrium is not altered. No response is generated to bind it. Response to agonist is decreased. If an antagonist has only slightly greater affinity for Ra than for Ri, the equilibrium is only modestly shifted towards Ra. A submaximal response is produced and the drug is called partial agonist. The inverse agonist has high affinity for the Ri state. Therefore, it can produce an opposite response provided the resting equilibrium was in favor of the Ra state. Certain ion channel receptors such as benzodiazepine receptor and some G protein coupled receptor like histamine H2 exhibit constitutive activation, that is, an appreciable intensity signal is generated even in the basal state, no agonist present. In their case, the inverse agonists stabilize the receptor in the inactive conformation, resulting in an opposite response. Only few inverse agonists are known at present. However, the receptors are now known to be capable of adopting not just two but multiple active and inactive conformation favored by different ligands. Figure 4.3 illustration of two-state receptors model. First is resting equilibrium Ra in equilibrium with Ri. Second is Ra agonist binds with Ra and Ra response in equilibrium with Ri. So first is the resting equilibrium, second is agonist, third is antagonist, where Ra binds with the blocker plus Ra in equilibrium with Ri binds with blocker plus Ri, no response. Partial agonists, Ra binds with partial agonist plus Ra and Ri binds with partial agonist and Ri, but the binding of Ra with partial agonist is more as compared to Ri, whereas in case of inverse agonist, Ra is free and Ri is bound to inverse agonist. Opposite response.